So this paper behind me, I think, shows the most exciting new theory on Big Bang cosmology, which explains all of the observational physics with simple classical general relativity and modern physics, just basic quantum mechanics. And it works like this. The initial singularity would have existed with all the laws of physics being present and some arbitrary number of fermions present. Things like quarks and electrons, those kinds of things would have been present. And in a Planck unit of time, they would have to make a quantum transition because they can't have all the same quantum numbers. This is called the Pauli exclusion principle. It's what keeps my hands from pushing through each other when I press them together, and my feet going through the surface of the Earth. Those valence electrons in those atoms, they can't overlap and be in the same position, or they have the same quantum number. And so it acts like a force to push them apart. Well, the arbitrary number of fermions present in the initial singularity would have to do the same thing. They have to move apart. And if it happens in a Planck unit of time, it happens at about 10 to the 20 speed of light. So it's extremely fast. And when that occurs in the second unit of Planck time, they have an enormous amount of energy. So the paper predicts that there's going to be around 10 to the 20 particles being created that are particles and antiparticles due to all the collisions. Just a massive amount of energy as these things have uncertainty energy and expansion energy. And once one of them interacts, when it's got this enormous amount of energy, like a particle accelerator, it just creates particles and antiparticles. And these will, in the second unit of Planck time that they're created, in the third unit of Planck time, they will annihilate. Matter and antimatter will annihilate within statistical fluctuation. Some statistical fluctuation will still be present that won't annihilate. And if you have 10 to the 20 particles, the square root of that is 10 to the 10. So in a single volume of a fermion that came out of those initial Planck time units, that fermion will then have 10 to the 10 other fermions present there of particles and antiparticles that then has to also do a quantum transition and expand. And this process keeps occurring, so you've got this critical reaction of particles being created due to the uncertainty energy, expansion energy, and the Pauli exclusion principle pushing them apart, so that it continues at these intervals of Planck time until light and gravity and gluons can catch up. So although it started much faster than the speed of light, eventually all of this energy is going to generate gravity, but it only travels at the speed of light. So as soon as it's able to catch up and pass through this distance of a fermion radius, that will eventually slow it down. So this process then has to continue until you're able to get right when that light speed starts to just go from one fermion to the other, and you're able to start getting attractive forces to try to attenuate this. You've got about 10 to the 120 particles, which is far more than the number that we have in the universe today that we know of. And so that this huge amount gives rise to what looks like a flat space-time as we look out into great distances. And because all of these started the same way, they have the same phase space, meaning that you see what we see everywhere, even though they weren't causally connected. Look to